It's time for Maths with Mr. Thomas.
Hey, here we go with Chapter 2, Lesson number 7, Higher Derivatives. Now, obviously, if we're given a function, y equals f of x, well, we can easily work out the first derivative, dy by dx, or f dash x. However, what we can also do is we could then differentiate dy by dx, or f dash x. And if you differentiate the first derivative, that gives you the second derivative. If you differentiate dy by dx, what you do is you would write that as this. And the way you read that is d2y by dx squared. Or if you were differentiating f dash x, you would have f dash dash x, or f double dash x. If you differentiate the second derivative, what do you think that gives you, Adam? Good, it gives you the third derivative. Would you believe it? And if you differentiate the second derivative to get the third derivative, well, the way you write that, you can either have it as d3y by dx cubed, or you could have it as f dash 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 x, or an f with a wee 3 and then x. So you can write it different ways. Let's try some examples then. So example 1, find the fifth derivative of y equals 2x to the power of 4 plus x cubed, take away 3x squared, plus 4x, take away 1. So for this one, Chuka, working out the first derivative. So we're given y, so we're going to have dy by dx. dy by dx, Chuka, would give you, perfect, you'd have 8x cubed plus 3x squared, take away 6x plus 4. Differentiate it the way you normally would. Brilliant. After that, Basit. Second derivative, how do you write that again? Good, d2y by dx cubed. d2y by dx cubed. And that would equal, all you do is you take your first derivative and differentiate once again. So that would give you 24x squared plus 6x, take away 6. And that would be your answer. Working out the third derivative then, Marta, what would that be? Yeah, you'd have d3y by dx cubed, and once again, bring the power down, take one off the power, blah, 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 right the way along, and you'd get 48x plus 6. Working out the fourth derivative. If you work out the fourth derivative, that would be just differentiating the third derivative. So you'd have d4y by dx to the power of 4, and that would give you, differentiate 48x plus 6, and it gives you just 48. Fifth derivative then, d5y by dx to the power of 5, differentiate 48 with respect to x, and that would just go to 0. So the fifth derivative just works out to be 0. Example 2, find the fourth derivative of f of x equals sine 3x. So for this one then, it's f of x, so the first derivative is going to be f dash x. And how would you work that out? Well, yeah, when you differentiate sine, well, you know sine goes to cos, so we'd have cos 3x. But remember the chain rule, you have to multiply by the derivative of what's in the brackets. So we'd have cos 3x, but we're multiplying by 3. So we'd have 3 cos 3x. From there then, working out the second derivative, so we'd have f double dash x, and that would equal, well, the 3 is just going to stay as it is, and if we differentiate cos 3x, well, cos would go to negative sine 3x, and again you multiply by the derivative of what's in the brackets, so we'd be multiplying by 3. That would then give you 3 times 3 is 9. We've also got the negative there, so negative 9 sine 3x. Working out the third derivative, so f dash 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 x, to get that, well, you could do this different ways. What I'd probably do is take the negative 9 to the side and just leave that as it is, and then think, right, well, if I differentiate just the sine 3x, what would happen to that? So differentiating sine, that would go to cos. 3x would stay as it is, but then it'd multiply by the derivative of the 3x, which would be multiplying by 3. From there then, I've got the negative 9 times 3 is negative 27, and I'd have cos 3x. Working out the fourth derivative, so f with a wee 4, and then x would be, well, again, you could do this different ways. You could either think, right, well, negative cos, if you differentiate that, it goes back to sine. But what I'd probably do is think, right, well, the negative 27, if I just put that to the side and ignore that, and then just differentiate cos 3x, because any numbers would just stay as they are. So cos 3x, if I differentiate cos, it would go to negative sine. So again, it'd have negative sine 3x, but you multiply by the derivative of what's in the bracket, so multiply that by 3. And that would give you negative 27 times 3, and you've got that other negative. So two negatives make a positive, and 27 times 3 is 81, so you'd have 81 sine 3x. And that would be your answer. Let's try another one. Example 3, given y equals 4e to the power of 2x plus 2e to the power of negative 3x, find d2y by dx squared. Mikoe, what would you do for this one then? How would you get the second derivative? Good, you'd have to find the first derivative. So the first derivative would be found by working out dy by dx. And if you differentiate this then, bit at a time, 4e to the power of 2x, well, the 4 would stay as it is. And then e to the power of 2x would just stay. E to the power of anything stays as it is. But what do you have to do, Mikoe? Good, you multiply by the derivative of what the index is. So that you would be multiplying by 2. With 2e to the power of negative 3x, the 2 would stay as it is. E to the power of negative 3x would stay as it is. And again, you multiply by the derivative of this index. So you'd be multiplying by negative 3. Just a recap from differentiating e to the power of x with that lesson. From there then, well, you've got 4 times 2, so that would give you 8e to the power of 2x. And negative 3 times 2 would give you negative 6e to the power of negative 3x. So that is going to be the first derivative. We want the second derivative though. So Taylor, how would you get the second derivative? Good, yeah, you just differentiate again. So differentiating 8e to the power of 2x, well, the 8 would stay as it is. E to the power of 2x would stay as it is when you differentiate it, but you multiply by the derivative of the index. So differentiate 2x and you get 2, so you'd multiply by that. From there, you'd be taking away 6, so negative 6 stays as it is. E to the power of something stays as e to the power of something, but again, multiply by the derivative of the index. Differentiate negative 3x, and you get negative 3, so you times by that. From there then, 8 times the 2 would give you 16, e to the power of 2x. Negative 6 times negative 3 would give you plus 18, and you've got the e to the power of negative 3x. And that would be your answer. Example 4, find f double dash x given f of x equals 2x plus 1 all to the power of 5. So once again we want the second derivative. Tega, what would you do? Good, so to get the first derivative you would just differentiate using the chain rule. Perfectly right. So differentiate outside the brackets, the 5 would come down, the brackets stay as they are, you take 1 off the power. So 5 comes down, brackets stay as they are, take 1 off the power. Good. Tega, you're perfectly right. What would you then do though? Yeah, multiply by the derivative of the inside the brackets. So differentiate the 2x plus 1. From there then, if you differentiate 2x plus 1, well, that's going to give you 2. So 5 times 2x plus 1 all to the power of 4 times by 2. From there, you'd have 5 times 2, which will give you 10, bracket 2x plus 1, close bracket, to the power of 4. That's the first derivative. You want to get the second derivative, so you just differentiate again. Derek, what would you use this time? Yeah, again, you use a chain rule. So the chain rule, once again, for the second derivative, you want to differentiate outside the brackets, and then differentiate inside the brackets, and multiply your answers together. So the 4 would come down and multiply by 10, so that would give you 40. Brackets stay as they are, but it would drop to the power of 3. And then multiply by the derivative of what is in the brackets. So you want to differentiate this 2x plus 1. From there then, if you differentiate 2x plus 1, well, you're still getting 2. So you'd have 40 bracket 2x plus 1 close bracket cubed times 2. And then from there, 40 times 2 would give you 80 bracket 2x plus 1 close bracket cubed. And that's your answer. Example 5, given y equals e to the power of x cos x, find d2y by dx squared. So for this one, Michael, what are you thinking? Product rule. Good, why are you thinking the product rule? Because you've got one function in terms of x times another function in terms of x. So yes, your product rule. If y equals u times v, dy by dx would be u dash v plus uv dash. So u is going to be e to the power of x, and v is going to be cos x. From there, e to the power of x, if you differentiate that, it would go to e to the power of x, good, it stays the same. Just remember to multiply by the derivative of the index. In this case, though, it's 1, so it would stay as e to the power of x. Differentiate cos x, and that is negative sine x, just from higher, good. Meaning then, dy by dx would be u dash v plus uv dash. So, u dash times v would be e to the power of x times cos x, plus e to the power of x times negative sine x. Obviously, with that negative there, you could swap that plus, so you'd have take away e to the power of x sine x. From there, you could go on and you could work out the second derivative from this, but then you would have to use the product rule on this part and on this part. What you're best doing is taking out any common factors. And the common factor here, Lewis, is e to the power of x. Good, e to the power of x, so take that out as a common factor, meaning we'd have e to the power of x times cos x take away sine x. And then from there, we can work out this second derivative, the d2y by dx squared. However, what would we have to use? Product rule! Perfect, we're using the product rule because we've got e to the power of x times cos x minus sine x. So, you're going to have u and v. U is going to be e to the power of x. V is going to be cos x minus sine x. U dash is going to be e to the power of x. It just stays as it is. And if you differentiate cos x minus sine x, well, cos x would go to negative sine x, and negative sine x would go to negative cos x. Perfect. From there then, you can work out the second derivative. So u dash v plus uv dash, u dash times v is going to be e to the power of x times cos x take away sine x. And then you're going to have plus u times v dash, so e to the power of x times negative sine x take away cos x. From there then, well, if you multiply out the brackets, that's going to give you e to the power of x cos x, take away e to the power of x sine x, take away e to the power of x sine x, and then take away e to the power of x cos x. And if you look at that, well, you've got an e to the power of x cos x, and then you're taking away an e to the power of x cos x. So it's going to leave you with negative 1 e to the power of x sine x, and then you're taking away another 1 e to the power of x sine x. So really, you'd be left with negative 2 e to the power of x sine x. And that's your answer. However, hold up! Why are we doing this? What is the whole point in this? Why are we working out a second derivative and third derivative and fourth derivative and whatever we're wanting? Why are we doing this? Well, one application, one purpose is that the second derivative can be used to investigate the nature of stationary points on the curve y equals f of x. At a stationary point, if you work out d2y by dx squared and it works out to be a positive value, well, what that means is that the stationary point is a minimum. So you'd have a minimum turning point. If d2y, if the second derivative by d2y by dx squared, if the second derivative works out to be a negative number, so if it's less than 0, then the stationary point works out to be a maximum turning point. And if d2y by dx squared works out to be 0, well, what that means is there's not enough information given. It could be a maximum, could be a minimum, or it could indicate a point of inflection, and you'd have to use a nature table to determine which. That is one purpose. It can also be used when dealing with velocity and acceleration. If you're given displacement, you can work out the acceleration of an object by working out the second derivative. So it does have various purposes, which we will look at later, and we will look at them in chapter 8 when we go on to look at functions and graphs, and also with further differentiation and integration. For now though, try this exercise on higher derivatives. It's in the workbook, page 28. Check your answers as you go. Any problems, just let me know. And if you need the workbook, send me an email and I will fire it out to you. Good luck. Bye.